In this unit that we're just starting now, we're going to learn something about organic chemistry. Now, organic chemistry is a huge topic. It can take up several years of college. So obviously we're just going to touch the surface of it, but just to get you a little bit of experience with it so that you at least know what the topic of organic chemistry is all about. And it's not probably what you think it is. Organic chemistry is really the study of carbon compounds. So while we do study life molecules in chemistry, and you kind of start with organic chemistry if you're going to talk about those, that's more a topic for biochemistry. But in organic chemistry, we just look at compounds that are made primarily of carbon, but also there's lots of hydrogen in them, some oxygen, occasionally some phosphorus, some sulfur. But we're going to start out by just reviewing what we know about carbon, since most of these molecules are going to be made of carbon. So let's remind ourselves what we know about carbon. Carbon's a fairly small atom. It has only 6 protons. Most of the time it has 6 neutrons and 6 electrons. And if you were going to write a Lewis dot formula for it, it would look like this. Because it has 4 valence electrons. Now that's very important to us right now, because we have to remember in this whole study of organic chemistry that carbon will always form 4 bonds. Carbon obeys the octet rule all the time. Carbon will always form 4 bonds in order to get 4 more electrons. It's not going to form any ionic compounds. It's just going to form covalent bonds, always 4. So it can sometimes form double bonds, and it can sometimes form triple bonds, but always there will be a total of 4 bonds on it. So if we're going to get started looking at some of its compounds, we're going to look at the prefixes and the suffixes that are used to name these things. So starting with prefixes, these refer to how many carbon atoms are in the molecule. So if there's 1 carbon atom, the prefix is meth. If there's 2 carbon atoms, excuse me, the prefix is F. 3 prop. 4 bute. 5, now here's where it's going to look familiar, pent. 6 hex. 7 hept. 8 oct. 9 noon. And 10 dec. So if you weren't in class or won't be in class when we do this, you might want to pause the video here and make sure that you get all that into your notes. These are what we call the prefixes. So the prefixes are what comes at the beginning of the word, and then we have to have suffixes. And there are 3 different suffixes depending on whether we have all single bonds or whether we have a double bond present or a triple bond present. So suffixes will be ane if there's all single bonds. We actually generically we would call these compounds alkanes if they're only carbon and hydrogen and there's only single bonds. We'll use ene. We'll use ene if there's a double bond, and we'll use ine if there's a triple bond. Now obviously if you get a big molecule you might have some single, some double, some triple, and that gets really complicated, and we're not going to get complicated today. We're just going to look at the simple scenarios where we have no more than 10 carbons all in one line, and if we're going to have double bonds or triple bonds, it will just be one of them. So you can see where this could get much more complicated than what we're going to do today. So make sure you've got all that down, and then we'll look at some examples. So let's say that we have a chain of carbons that has 6 carbons in it. 1, 2, 3, 4, 5, 6. Now we know that each carbon has to make 4 bonds. That's really important. I'll say it over and over. Carbons will always make 4 bonds. And so therefore, if a carbon is not bonded to another carbon on all four sides, which it's not going to be in the compounds we'll look at today, then you have to fill in with hydrogens. So that means that this carbon is going to need 3 more bonds, and that will be to hydrogens. This is going to need 2 more, also to hydrogen. So there we have our first example of an alkane. All single bonds. So we count the carbons. 6 carbons means that we're going to start with hex. All single bonds means we're going to end with ene. So we have hexane. Now if we were to change this somewhat, so we're going to lose one of the carbons there, replace it with a hydrogen. We will rename this pentane. And you could keep doing that. You could put all different numbers of carbons in there, and depending on how many you have, you're just going to change the prefix to the appropriate one that we listed on the board a minute ago. Now let's get a little more complicated and say that we're going to put some double bonds in, or a double bond. And let's just say that I want to put a double bond right here. So that means that I'm going to do this, and right away I've got a problem, because now this carbon and this carbon each have 5 bonds, and that is against the rules. So what they're going to do is lose their hydrogens. So if there's a double bond there, the carbon will only have 1 hydrogen on it, and then it will be bonded to just the other carbons. And that means we have to change this. Now I haven't changed the number of carbons, so I'm going to still call it pent. But I have changed the way it's bonded, so now we have pentene. Now you can see that there might be other possibilities for pentene, because I might have put the double bond here, and that would be a different molecule altogether. If I had put the double bond here, that would not be a different molecule, because we have 1, 2, 3, 4, 5 carbons here, and right now the double bond is between, if I started numbering over here and I said, okay, here's 1, here's 2, it's between 2 and 3. Now, what if I started numbering over here and I said, here's 1, here's 2, and I put the double bond between 2 and 3? It's the same molecule, it's just turned around the other way. And you can think about that some if you want to, make a little model of it, draw it out, but putting the bond here and putting it here is actually the same thing. It's just looking at the molecule. Imagine that you could go around the back of the whiteboard and look at it from the other angle. It would be the same molecule. However, if you put a double bond here, that's different, because now it's between carbons 1 and 2 instead of between carbons 2 and 3. You always, by the way, you always start numbering at the end that will give you the smallest number. So that's why I did that before. That's why I started numbering over here. So if I number over here 1, 2, that's going to say that the double bond starts at carbon number 2. If I started numbering over here, I'd say 1, 2, 3, and the double bond would start at carbon number 3. So given those two choices, I have to start down here. I have to start in the place where the first carbon it will be numbered, will have the lowest number possible. So the one I've got written here is going to be called 2-pentene, because here's my choices. 1, 2, okay, this is the first carbon that's attached to the double bond, or I could say 1, 2, 3, and this is the first carbon that's attached to the double bond. So I start down here because this gives me a lower number. That's why. And if I walked around the back of the molecule, kind of do this in your head, walk around the back of the molecule and look at it from this side. Now this is on the left for you, and you would count 1, 2, and so it's really not as weird as it seems. It doesn't make any sense to say start counting from the left, because all you'd have to do is walk around the other side of the molecule, and the other side of the molecule would be on the left. So we have to say start counting in the place that will give you the lowest number. All right, so let's say that we want to change this, and I'm going to make the other isomer of pentene, and I'm going to make 1-pentene, and that means that I'm going to put the double bond here. So now I have some adjusting to do. These are going to get their hydrogens back. And these two are going to have to lose their hydrogens. And now that is called 1-pentene. And it would be the same molecule. I'd still call it 1-pentene if the double bond was down here attached to the carbon on that end. Let's try another one. Now this time I'm going to write it out a little bit differently because sometimes you see them this way. CH3, CH, CH, CH3. Okay, now the first thing I want to do is draw this out to show all the bonds, because now I have to figure out where is the double bond. And I'm going to do it based on the number of hydrogens attached to each carbon. So this carbon's got these 3 hydrogens attached to it. So I know that that's going to be like that. This carbon's only got 1 hydrogen attached to it. This carbon only has 1 hydrogen attached to it. And this carbon is 3. Now, based on that information, I say to myself, I know that every carbon has to have 4 bonds. And therefore, I look at this and I say, well, this only has 3 and this only has 3. So now I know that that's got to be a double bond. And I knew that because if it hadn't been, this would have been a CH2 and a CH2. So now that I look at that, I've got 4 carbons. So my prefix is bute. I've got a double bond. So my suffix is ENE. And now I have to look at, is there more than one place to put this double bond? And can I get a different molecule if I move it? And the answer is yes, because right now it's in the middle, but it could be on one of the ends. And so there's really only 2 possible ways that we can get butene. In this case, we're going to have 2-butene, because we'll number this carbon carbon number 2, or this carbon carbon number 2. Kind of doesn't matter. You get the same answer either way. All right, let's try something else. Let's say we'll just keep this, and this time, well, let's just redraw it because I've made a mess. Okay, CH3, C, C, CH3. Okay, so this time I drew little dashes in there that represent bonds. Sometimes they're there, sometimes they're not there. Don't worry about it. Doesn't mean anything different. So this is going to be carbon with 3 hydrogens around it. This is going to be carbon, carbon, carbon with 3 hydrogens around it. All right, what have we got here? Now, I'm not given any more hydrogens, which means that each of these needs to have some more bonds, but I can't put any more hydrogens in there. And if every carbon has to have 4 bonds, that's going to require a triple bond between those 2 carbons. So now we have, let's see, again we have bute because there are 4 total carbons. Now we have a different suffix because there's a triple bond, so we're going to have to go butyne. And is there a different place that that bond could go? Yes, it could go here and make a different isomer. So now I'm going to have to say that's 2-butyne. So let's just, for the sake of getting some practice, let's say that they gave me 1-butyne and asked me to draw it. So what I would do with this is say, well, I know that I'm going to have 4 carbons because of the bute, so I'm going to just draw those out first. I know that I'm going to have a triple bond someplace, and this tells me where. It's going to be attached to the first carbon, so let's just put that in. And then I'm just going to fill in with hydrogens, knowing that every carbon has to have 4 bonds. So this carbon's going to have 1 hydrogen. Let's see, this one's already got 4 bonds. We're going to need like that. So now every carbon has 4 bonds, and we have 1-butyne. Now, I got to show you something else. If you have a single bond, put the hydrogens in. Sometimes we get lazy and we just draw the dashes, and you'll see that in books even sometimes, because it's understood. If you're an organic chemist, you know this hydrogen's there, and if you just see the dash, you know, okay, that means this hydrogen's at the ends of those dashes, and somebody was too lazy to put them in. And I will probably do that sometimes on the board. Now, what is the geometric shape around those carbons? We learned this a long time ago. A carbon with 4 bonds around it will make a tetrahedral shape. So these are not flat on the board. These are tetrahedrals, 2 tetrahedrals as a matter of fact, stuck together. Now, around this bond, we have what's called free rotation. These atoms can kind of rotate freely around, and in class, I'll have models and I'll show you how that works. However, if you put a double bond in there, you no longer have free rotation. So let me show you how that works. I'm going to have to get rid of all this. Remember trigonal planar? This is what happens when you have 3 electron clouds around the carbon. You have trigonal planar. There is no free rotation around this bond. Meaning that if I had, let's say I had a CH3 up here, but only a hydrogen here. I'm putting H3C so that I can show the bond attached to that carbon. You'll see that sometimes. That's all it means. It means that these 3 hydrogens are attached to that carbon. It means the exact same thing as these 3 hydrogens attached to that carbon. I could have drawn it over here. Doesn't matter. You're going to see it both ways. Don't worry about that. Okay, however, this molecule is not the same as if these 2 switch positions, because there is no free rotation around that bond. So this is what we call the cis, C-I-S, the cis isomer. An isomer is one form of a molecule where there are other forms that are isomers of that molecule that have the exact same atoms, but there's just something different about the way they're bonded together. So we have the cis isomer here, and so let's see, can we name this thing? 1, 2, 3, 4. So we'll call it bute. Double bond makes it butene, and the fact that the double bond is on carbon number 2 makes it 2-butene. So now we have all kinds of pieces to this name. We know it's bute because of the 4 carbons, it's ene because of the double bond, it's 2 because the double bond is in position 2, and now it's cis because it forms this kind of arrangement. All right, so let's change it to the other one, which would be putting CH3 down here and a hydrogen up there. Now it's not cis anymore. Now it's trans. So we have trans 2-butene as opposed to cis 2-butene, and they are actually different. So if you're drawing the molecule, let's see how you would get there. Let's say that I gave you the name trans 3-hexene. Does that make sense? 1, 2, 3, 4, 5, 6. I'm not sure there is a trans 3-hexene. Let's make it a trans 3-octene. And the reason that I say that I'm not sure there is one is because I think 1, 2, 3. Oh, maybe there is. Sometimes if you get a number that's too big, you're too close to the other end of the molecule, and you get a smaller number by counting from the other end. So for example, there's no such thing as trans 7-octene, because that would mean I should have started counting from the other end of the molecule. However, I think I would have been okay, but that's all right. Let's go with this one. So first of all, I know that I'm going to have 8 carbons, but I'm not just going to draw them out in a line this time. I'm actually going to start by saying, okay, there's a double bond someplace, so let me just draw the double bond first. And then let's do this, because I know that it's going to take that shape. And then let's now put in the rest of the carbons. So I know that this has to be carbon number 3. So I can put a carbon over here and over here. And then I know that I want a total of 8, and I've already got 4. So I'm going to need another 4 down here. And I picked down here because of the trans. Okay, so now it's easy to fill in with the hydrogen. So I can just do this, and I am going to be lazy on this one and just do some dashes. So now we have an arrangement that shows where all the bonds are, and you know that there would really be hydrogens all the way around that. But that's how you can start with a name and draw the molecule. I always like to start with the double bond and then figure out what's going to go on each side of it, because otherwise you try to start from one end and you can get really lost and you end up having to get out the white out and start all over again. So that's one way to make that work for you. And I think that is probably as far as we are going today. So next time we'll look at some functional groups, which are other parts of the molecules that have things other than just carbon and hydrogen.